Which formula? Oh, I did that. Oh, good. Okay. Let's continue. So, yes, I remember. Maybe Zach or Diego, one of you were asking me about the constant or something, or the moles. Yeah, yeah. Come on, where are we? Ooh, we got it. Okay, here we go. So you got these two formulas last time, yeah? Yeah. So you notice that in the first case we're using moles, and the second case we're using number of molecules. Now, let's have a look at the formula here. So if I said PV equals N or T, oops, okay, and then let's say I do something like, oh, I don't know, that's number of moles. So let's say I change this into N times Na times or over Na times T. So what have I done? I've just put in an Na and an Na, haven't I? Now, let me call this guy here K, because it's a constant over a constant, isn't it? What constant is Na? Avogadro's. Now, what is N times Na? 1. N times Na? Oh, guys, wakey. No, it's not. Oh, goodness sake, guys. The number of moles times Avogadro. Thank you. Number of molecules. Isn't it? Yes. Isn't it just? And T. So, my point is that this formula and this formula are really the same formula. Oh, I want to check the dimensions actually of these constants before I continue. So, in the first formula, you can say or equals PV over NT. And in the second formula, you can say K equals PV over NT. The units for or would be pressure is Pascal's. Well, do you know what? Pascal's is newtons per meter squared, and volume is meter cubed, and N is moles, and temperature is Kelvin. So that would be Newton meters. Yeah. What's a Newton meter? No. Oh, torque. True, and another unit. Newton meter? Joule. Joule per mole per Kelvin. Okay. What's the only difference here? The N is the number of molecules. So you could just say it's joule per Kelvin. Okay, so these are the two units here for them. But I think I give that here. Anyways, dividing, we see that these formulas are the same, just with a different constant if we're using different units. We call the or the ideal gas law constant, and does anyone know the name of the K? No, that's okay. And the K is called the Boltzmann constant. Now, what I find interesting is they're really the same thing, just with different units. Can you see? The difference is or over Na is K. So, I mean, there's hardly any difference. Why the need for two constants? I don't know. Anyways, here are the values of the two constants. I find it very peculiar that there are two different formulas with two different constants, even though they're the same thing. You know, it would be like me saying, oh, here is Newton's formula, F equals ma if you're using kilograms, and here is Newton's formula if you're using grams or something. You know, it seems very odd to me that there should be two different formulas just because of two different units. I don't know. I really don't know. It's very confusing. There might be a good reason for it. Anyways, what you need are these formulas and these constants. Oh, and finally note that we always use Kelvin for temperature.
Has also another constant, right?
Boltzmann probably has a few things because he was a very big scientist about 100 something years ago.
There is another one called the Stefan Boltzmann constant, which is 5.6 or something.
What's that constant for?
Just it says it's on the list of my calculator.
Work per meter squared.
Is it something to do with light?
Kelvin to the fourth.
Maybe something to do with radiation. Anyways, that doesn't come up on this course, just the what's called the Boltzmann constant. On the calculator, I think they represent it as KB, I think, on the calculator. Do you have the Casio 991?
No, it's just K.
Oh, is it just K?
Yeah.
K for me also.
Okay. I thought they wrote it as KB. Oh well, okay. Continue. You have this? Yeah? Zach? Yeah, you have this? Okay. Right. Some molar masses you'll need. And the structure. So liquid water, you know the structure. It's 2 hydrogen and 1 oxygen. And the molar mass is 18. Now you might need to know that for some of the questions, so you probably should write this table down. What did you do last week with Lorraine? Have you started this yet? No. Okay. I'm having trouble with my smartphone
What's wrong?
because I'm using a VPN. My email people blocked me.
Did you know about it?
Yeah, because they thought, oh, security risk. He's checking in from Venezuela or something, you know. Right, next one. Do you have that? Carbon dioxide. Much heavier.
Carbon dioxide is heavier than water.
Yeah. Well, it's molar mass. Why?
For the same number of molecules.
Oh yeah, yeah. I guess oxygen maybe is what's adding to the weight a lot. I don't know.
Well, carbons are 4 hydrogens.
Oh,
4 hydrogens.
carbon has 12 in total.
Yeah, 12.
Oh yeah, well, hydrogen only has 1.
1.
That's the reason. Okay, next one. Yeah. Hydrogen. Now, did you learn this in chemistry, that hydrogen when it's in a gas form is H2?
Yes.
Yeah. Do you know the name of this? when a gas pairs like this?
What do you mean?
Well, I mean, I think there's, yeah, that's it. There's gases that occur in pairs, like H2O2 and so on. Does this have a name in chemistry?
Probably does.
There's some type of something, dielectric, something, bond, something, I don't know. Anyways, when you do it with Lorraine, you'll find out if it has a name. But how many atoms are like this that occur in pairs in a gas form?
H2, N2, F2, I2.
Guess so, how many?
I don't know, CO2.
O2. Argon?
Yeah.
I don't know which they are, I just know how many there are.
6,
Close, 7.
7. So
What's
what's
the
like
last?
iron in this, bromine as well?
I have no idea. I only know the ones we use, which is O2 and H2 and so on. Next one is helium.
Or nitrogen.
N2 is as well, yeah. Helium, which is... Oh, Harry, can you let him in, Doc? Thank you. Oh, Harry, you're late again. This is starting to become a problem. Okay, next one is oxygen, O2. And finally, nitrogen, also a pair, N2. Okay, you got all those? Yeah? Yep, okay. Right, so we have a big example to do, but it's a good example because it covers really everything we need. So let's do this one together. A cylindrical, so what shape is that? So that's like this type of shape. Gas tank of, let's just say, of radius 30 and height 1 centimeters and 1 meter is filled with helium. So let's draw that to get started for our problem. Woohoo. Right, so we have a cylinder and its height is 1 meter and its radius is 0.3 meters and it's full of helium, which is, yeah, helium I said, He, yeah. The tank is in a warm room of temperature 26.85. Job 1, let's convert this to Kelvin. So, what is the, what is the temperature? It will be 300 Kelvin. That's why I picked 26.85, I'm sure, to make it 300 Kelvin. Right? Anyone disagree? No? Can you also calculate for me the volume, which is using the formula pi r squared h. So what is the volume here? Meters cubed. Are we happy so far? Yep. Right. And therefore the tank is at this temperature too. The tank is under a pressure of 3 atmospheres. Now, we need to convert atmospheres into pascals. So you have it in your notes. I think we said 1 atmosphere is 101 point, what was it? 101 point something 325, is it? I forget.
101, 325.
Kilo.
Kilopascal.
Yeah, so 3 times 101, 325. What's that, please?
That's pascals.
That's in pascals, yeah, what's that? So 303,975, isn't it?
Yeah.
So if we do 4 significant figures,
304.
that would be 303. No, it'd be 304, wouldn't it? Yeah.
304.
304,000. Do I have the right number of zeros?
Yeah.
Yeah. Pascals. Okay. Now we can answer the first question. A part 1. How many moles are there? Right, well, that's using the formula PV equals N or T. So then that means N is PV over RT. The pressure, we know. The volume, we know. The R, we know. And the T, we know. So off we go. Using your calculator, give me the N, please. Moles. Okay, part 2. How many molecules are there? So how do we get that? The number of helium molecules. What do we do? Yeah, 34.45 times Avogadro, which is 6.02 times 10 to the 23, isn't it?
2.074 times 10 to the 25.
10 to the
25.
number of helium. Next. How many helium atoms are there in the tank? Well, there's this many molecules, right? No, I don't think for helium, it's this 1, isn't it? So it's also the same because of its structure. Now, if it was something like hydrogen, what would you do, Dorian? You times by 2 then, yeah. Or if it was oxygen or something, yeah. Right. Next one. Some gas is allowed to escape from the tank. The new pressure is 2 atmospheres. How many moles of helium are now in the tank? Right, well, that's kind of similar to which question we did earlier.
1.
It's the same as number 1. The only difference is you have to change,
Pressure.
yeah, change P to 2 times 101,325. So we'll get a different value for N. I'm sorry, I hope I'm not going too fast. Is this all okay?
Yeah.
Is this okay, Dorian? Yeah. So what do we get for the new number? It should be something like about 20-ish. Because it should just be 2/3 of this number. What did you get, Zach? Yeah. Lynn, can you do 2/3 of this number? That's the quickest way to get
Where
it.
is the syntax here, please? 22,97.
Thank you, Zach. Oh, he retyped in this formula, but I knew that the answer would work out to be the same as 2/3 of this number. Because the only thing that changed is this P went from 3 atmospheres to 2 atmospheres. So it's just mathematically, I know the answer will be 2/3 of this, but he used the proper formula here. Okay, so part 2. How many escaped? Oh, well, okay, that's easy. How many escaped? Yeah, how many moles escaped? So that would be 34.45 minus 22.97. That's how many escaped. Part 3. So, guys, what's happened now is we had the tank, and it was had 3 atmospheres of pressure, but then some of the gas escaped. So now it has only 2 atmospheres of pressure, and you have this helium floating around now. Okay. My next question is, what's the volume of this helium? What's the volume of the escaped helium? So, by using this formula, we can get V equals N or T over P. Now, what's the N? 11.48. What's the R? 8.31. What's the T? 300.
Yeah.
But what's the P?
1.
Correct, 1 atmosphere. Why?
Because it's ambient.
Ambient, yeah, it's in the surrounding room of 1 atmosphere. Yeah? Sneaky, huh? Okay, so what's the volume here?
How come I is 8.3?
Isn't that the or constant?
Isn't it times 10 to the sum?
No, I don't think so.
0.282.
No, don't tell me you've been using the wrong or all this time.
No, I haven't been.
Okay.
R is 8.3144.
Yeah. Correct. What's this number?
0.2.
Thank you.
Yeah.
Yeah? Okay, good. Right. Lastly, C. If the tank was left open until no more helium escaped, then how many moles of helium are left in the tank? No, because that would mean there was a vacuum, which obviously doesn't.
There's 1 atmosphere.
That's it, very good. There'll be 1 atmosphere of helium in the tank, because it's not going to drop below this, because otherwise that's it. The tank starts to shrink in as the helium spontaneously leaves. Do you get it, Zach? That there 1 atmosphere of helium will remain. It's a little bit like, what's the example you can think of at home?
So any aerosol can will be empty essentially when it's at equal pressure.
Yeah.
So it's never really empty.
Correct. Yeah. Which kind of sucks because you paid for it. But you're right. I mean, the only way to truly empty it is if you start to crush the can.
Yeah.
Which perhaps you could do.
They're pretty strong to hold that amount of pressure anyway.
Oh, that's true. Yes. Put it in some crusher or something. I don't know. But you're right. Now, what'll happen is in real life, eventually all the helium in the tank will exchange place with the air in a sort of slow,
Via osmosis.
yeah, some kind of process like this, right? Because you notice from your experience of having balloons that eventually the helium will seep out and be maybe exchanged with air molecules. It's difficult to keep helium contained. So let's work this out. The formula is N equals PV over RT. The pressure is 101,325. The volume is 2827. The ore is 8.31 and the temperature is 300. So what's that about? It'll be something like 11.48 or something. 41 moles of helium. For what? 49. Okay, are we happy with that example? Very long example, but I like it because it covers all the sort of
So the
main
thing you
things.
just have to look out for is like times equal like 2 fill.
Just to watch out for the structure. Yeah, yeah, yeah. Usually the exam question is a bit more explicit with the pressure. I was being a little bit more cryptic by not telling you that the room was at 1 atmospheric pressure, which is a reasonable assumption to make. Just like it's reasonable to assume that the room is at ground level and the G is 9.81. These are reasonable assumptions. Yeah? Any questions with this one? You'll be doing lots of this stuff in chemistry. Do you need to write anything down from the question, or are we okay? Is this one okay? Yeah. Yeah? So how are we doing for time? Oh, good. So what we'll do is I'll give you time to now try these questions. I think you should have a good few of these. Let's have a look. Because it's kind of a standard physics section A question.
There's no control.
Problem?
Can we look back at the notes?
Nice.
My handwritten stuff? Yeah, there you go.
No, sorry, not the notes, the slides.
Which slide do you need?
PV
PV equals nRT.
Yes, that's
What's wrong? What?
no, because we missed out something.
22.
Something critical?
22
Yes.
questions.
Nice.
Yeah, nice.
So you know what that means, don't you? Pretty much guaranteed to have this in your
Exam.
exam.
Oh, that's good if you're good at it.
Yeah, you do it in chemistry as well. Should be able to bank this question. Let me have a look. Generate worksheet. Ideal gas law. Let's have a look. What's the first one? Let's see.
So K is R over Avogadro.
Yes,
Yeah.
pretty much. In question 1, so it says here that you know that temperature represents energy, and the molecules are at 40, and you think that's twice the energy than at 20. What's wrong with this statement? So, if you look here, I gave you a formula, PV equals N or T. Yes? And I think I also gave you the formula E equals, wasn't it E equals 3 over 2 PV? Wasn't that it? So therefore 2 over 3 equals PV, true? Guys, are you looking? Yeah. So therefore 2 over 3E equals N or T. So this is a constant if it's a gas, and this is a constant. So that can lead you to say that E, or rather Ke, since there's no potential energy, is proportional to temperature. So the question seems right. You double the temperature and you double the kinetic energy. However, what mistake is made in this question? That's it. But this is only true if T is in kelvins. Otherwise it's doesn't work to say it's proportional in Celsius. And the reason is this formula works only in Kelvin. So the answer to the first question is, this statement is wrong because this relationship is only true when temperature is measured in Kelvin.
Wouldn't. Alright. Because if they're in Kelvin, it wouldn't be double.
Exactly, the difference would be much smaller. The difference between 20 and 40 Celsius in Kelvin is only like 10%. So it's probably something like it'll have 10% more kinetic energy, you know. If you convert it into Kelvin, you can get the percentage increase more precisely. So question 1 is okay. And question 2 is okay. Alright, so you have 10 minutes. See how many you can do in 10 minutes. Regina and Dorian, can I close this? Do you have everything you need?
Yes.
Are you sure? Okay. What did you miss on this slide?
Constants.
Ah, okay.